So the last part of our review here is going to be looking at line and rotation symmetry. So these are different kinds of symmetries that we can have in our shapes. So for the rotation symmetry first, let's build a regular polygon. We're going to make it a hexagon. So give it 2 vertices, say that's a 6-sided regular polygon. Here we go. Just going to hide these labels to make the diagrams a little more clear as we're going forward. I will ask that we make note that the 2 vertices we made our diagram with, these blue dots on the bottom, are blue. The other vertices that the computer generated are gray. So note that our starting point has 2 blue vertices on the bottom. Now let's say we want to rotate this about the very center of the image. So we need to find where that center is. Well, if we connect our diagonals, that's where they intersect, is in that center. So we'll put a point there. And again, we'll hide the label. So this is our hexagon with some lines drawn in just to verify it. So now it really looks more like 6 triangles. But if we have rotational symmetry, right? There was a study of line and rotational symmetry. Rotational symmetry means there's a way to rotate this shape so that it looks exactly like it did before. So if we select the shape, say we're going to rotate it about that center, if we rotate it counterclockwise 45 degrees, it doesn't look exactly like it did before. We have 2 different hexagons here. They do not line up perfectly. If, on the other hand, we do our rotation not in 45 degrees, but in 60 degrees, because that 360 degree angle in the middle has been broken into 6 pieces, so each of these lines are 60 degrees apart. I hit rotate. At first, it doesn't look like anything has happened. The shape looks absolutely identical to what it looked like a moment before. But a moment before, the 2 blue dots were on the bottom. Now, one's up on the side. That's because the blue dot we had here has now moved to the next one. If we start showing labels, this is B, right? We've got C, A. We have our labels here on the original shape, which still has not been rotated. But these blue dots are no longer A and B, they are BC, because we have a new shape on top. So that is a rotational symmetry. Now, things can have rotational symmetries, but they have to be about a particular point. So we'll just hide all these labels again. So this rotational symmetry actually only works if we are rotating about that center point by exactly 60 degrees. We see what happens if we rotate by 45 degrees. It doesn't line up. If we go to this side and rotate by 60 degrees, that doesn't work either. That rotates our hexagon, sure, but that doesn't line up perfectly with where it used to. 2 points do, the rest do not line up. So any shape will have 360 degree symmetry about its center, but only certain shapes have more symmetries than that. So you can pick a point within a shape, rotate it around that point 360 degrees, and it's going to look exactly like it did before. And that will be true no matter what your polygon looks like. If we do this sort of funky and wild, completely asymmetrical version, and we rotate it about a point, so we highlight all of these, rotate it about this random point. Okay, the point has to be defined. And we rotate it by 360 degrees. All of our points have been labeled with that primed to say it's transformed. But other than that, this looks absolutely identical to what we had before, because a 360-degree rotation lines it up exactly as it used to be. So that is our rotational symmetry, where we can rotate it and it looks the same. But what about line symmetry? That's the other symmetry we are looking at. So let's take, this time, a 5-sided polygon. So we'll take a pentagon. I forgot it draws it from the bottom by default. If we have a reflection in a line, say from here to here, right, we select our shape, and then we have to pick a line to reflect about. I suppose that would help if I drew the line first. So let's take our lines. Let's see if we find a bisector of the angle. So let's start with an angle bisector. If we take that angle, here's that angle bisector, and we'll bisect this angle. Here we go. So these should now be intersecting in the center of the shape. I'll just stick one at every point. So if we could have a line symmetry about any of these lines we've just made. If we reflect this shape about this line, it looks just like it did, even with the A and B equally spaced. If we reflect the same shape about this line, and again, it'll be the same thing. We see a slight darkening as they're adding more pentagons on top of the ones that we already had. Right? Each time we do it, there's one more layer of that blue pentagon that makes it just a little bit darker. So as long as we're reflecting on those lines, we have that symmetry. So every regular polygon will have line symmetry bisecting each of its angles and each of its sides. Now, it won't necessarily have line symmetry about other lines. If we just pick an arbitrary line here and then decide to reflect it about a line, again, we pick this shape, we pick this line, and we see it's not a perfect fit because that line did not go through a point or through a side. So that one was not a bisector. And it has to be a bisector. We could do a line from E to C. That one does not bisect either angle. So if we try to reflect this shape about that line, that's also not going to line up. So that is a key component of this line symmetry. That line must bisect at least one of the angles or the sides, ideally both. And in fact, in a regular polygon, you cannot even create a shape that only bisects one of those. It has to bisect both. But what about an irregular polygon? So let's say we have a rectangle here. Just forcing it to be a rectangle. Now I said we could have symmetry as long as we're bisecting an angle or a side. So if we do a perpendicular bisector to that line, or a perpendicular bisector to this line, these will produce symmetries. If we reflect about a line, reflect the shape around this line, it looks the same. Reflect the shape around this line, it looks the same. But if we try to bisect an angle, and we reflect it on that line, that is not going to be symmetrical. So with an irregular polygon, it must bisect in a way that produces still has a line of symmetry. If we reflect this shape about this line, we still get a rectangle. So it's a similar shape, but this is not a line symmetry because the two shapes do not look identical. Nor will it work if we try to set it up. Let me back up to our original shape. If we try to just go across the diagonals, which are another tempting idea, again, that's something that can work in regular polygons, but if we try to reflect around that line in an irregular polygon like a rectangle, it is not a line symmetry. The two graphs do not look identical. So those are the key shapes here. Now the reflection and transformations content isn't a huge part of Math 20-2, which we're reviewing for, but it is going to be a rather sizable part of the first chunk of Math 30-1, although when it shows up in 30-1, it's more the algebraic approach than the graphical approach. We will be reflecting curves around lines rather than shapes.